Welcome to a Chem 101 lecture about naming ionic compounds. We're going to use the IUPAC system, which is the International Union of Pure and Applied Chemists. And first we'll start with monoatomic ions. Monoatomic means they are composed of one atom, and when we deal with anions, the simple change is to change the ending to "ide." So for example, the sulfur atom goes to the sulfide ion. For a monoatomic cation, there is no essential change. Sodium atom would go to sodium ion. So here are some examples. If we had aluminium 3+, that would just be aluminium ion. If we had strontium 2+, that would simply be strontium ion. Nitrogen 3- becomes the nitride ion. And iodine 1- becomes the iodide ion. There's a list in your textbook of polyatomic ions that you should memorize. Some of them are very unique, like ammonium ion or hydronium ion. These are shown at the top and are cations. Other ones are anions, and the acetate ion is shown here. That's actually part of vinegar. You're probably familiar with the hydroxide ion. The others of these, many of them follow a pattern that we're going to discuss that's related to their oxidation state. Here are the rules for naming oxoanions. These, of course, are anions which contain oxygen. There's a set of rules if the central atom is not group 7. If that central atom is in its highest oxidation state, the ending of the oxoanion is 8. If we have one less oxygen atom, the ending in the oxoanion is ite. Here's two examples. Oxoanions of sulfur. Sulfur can exist as SO4 2- or SO3 2-. The Lewis structures are shown here, and there will be more detail on that when we get to Chapter 5. However, you can see that sulfur's in the center, surrounded by oxygens, and the entire structure has a 2- charge. All right, let's look at the oxidation states. You probably remember that oxygen is a -2 charge. So when I start to think about how to figure out the oxidation state of the sulfur, remember that this has to add up to -2, and that each of the 4 oxygens is -2, so that gives me a -8. So I think we can see that +6 - 8 gives us -2. Now, since sulfur is in group 6, and its oxidation state is +6, this material is named the sulfate ion, with an ATE ending. If I do the same thing for SO3 2-, you will find that the oxidation state is +2. Since it has one less oxygen atom in the structure, we call that the sulfite ion. So here's an example. What is the oxidation state of carbon in CO3 2-, the group carbon is in, and the name of the polyatomic ion? All right, I think we can probably guess that yes, carbon is in group 4. Let's look at the oxidation state. We know it has to add up to -2. We know that each oxygen is also going to be -2, so that's going to give us a -6. So something -6 equals -2. So I trust you realize that is +4. And since the charge matches the group number, I believe we need an 8 ending. And I think we should probably call this carbonate. How about the oxidation state of nitrogen in NO2 1-? The group nitrogen is in, and the name of the polyatomic ion. All right, group number is not in question. That's group 5. Let's look at the oxidation state. So we are dealing with NO2 1-. The charges must add up to 1-. Each oxygen is a -2, so that gives me a -4. So something -4 gives us a -1. I hope you believe that's a +3. And it certainly is. So since the oxidation state is +3, but the group is +5, we have an ending of -ite. Now, what about oxoanions that have hydrogen but are still overall negatively charged? For example, HPO3 2-. All right, it's easiest to do these problems by removing the H and making the charge negative by 1 more. So you notice we've gone from HPO3 2- to just PO3, and now the charge is 3- because I have made the charge more negative. Now I can effectively name that material as phosphite. How do I do that? Well, the charge is -3 on the molecule. I know that 3 oxygens at -2 must be -6. So therefore, the phosphorus is +3. But what group is phosphorus in? It is in group 5. So because of this difference in group and oxidation state, we have ourselves an -ite ending. So if the deprotonated one, where we've removed hydrogen, is phosphite, then we can just name the one with hydrogen hydrogen phosphite. It can also be called biphosphite instead of hydrogen phosphite. This question asks us about the oxidation state of selenium in HSeO3 1-, the group selenium is in, and the name of the polyatomic ion. So the group is not in question. We are obviously in group 6. If I were to remove the hydrogen from this and make the charge more negative by 1, this would be SeO3 2-. So let's figure out the oxidation state. It's going to have to add up to -2. 3 oxygens at -2 will give me a -6. I think I can see that +4 has to be the oxidation state of the selenium. So remember, if we're in +4, but the group is 6, this gives us an ending of -ite. So we know it's not that one. We know it could be this one, except we're missing, of course, the fact that we're being asked about HSeO3 1-. So it has to be answered D. +4 oxidation state, selenium is in group 6, and we have acknowledged the hydrogen present as hydrogen selenite or biselenite. Now, what if we're dealing with oxoanions in which the central atom is group 7? We're still going to use the idea that 8 is higher than ite in terms of oxidation state. But we need something to say super 8 and lower than ite. So we also have prefixes. The classic example is oxoanions of chlorine. Chlorine with oxygen has 4 different oxoanions. And I can go through and think of the oxidation state. If I start with ClO4 1-, each oxygen is -2. So that means the chlorine has to be +7 oxidation state. That is the biggest oxidation state that chlorine can have, since it's in group 7. So we would call that the perchlorate ion, because it's the highest oxidation state. If we had one less oxygen, the oxidation state of the chlorine would be +5. So now we just call that chlorate ion. If we had one less oxygen again, we would be dealing with a +3 chlorine oxidation state, and we would call that chlorite. And finally, if we were missing all but one of the oxygens, the oxidation state of the chlorine would be +1, and we would use the prefix hypo to give us hypochlorite ion. So here's an example. What is the oxidation state of bromine in BrO3-, and which group is bromine in, and the name of the polyatomic ion? Okay, once again, group number not in question. So if we look at BrO3-, we have to add up to 1-. The 3 oxygens at -2 must be at -6. So I do believe we're at +5. +5 oxidation state, so not answer B, certainly. And since it is the second highest oxidation state for bromine, we would be calling this bromate. So +5 oxidation state, bromate. How about bromine in BrO2-1-? Once again, we're in group 7. So if we look at BrO2-1-, of course, the sum of the oxidation states must add up to -1. Each oxygen is going to be -2, so that leaves us with -4. So +3 is going to be our oxidation state of the bromine. So certainly not answers C or B. All right, since +3 is the sort of third highest oxidation state, it's going to have an ending of -ite. So that one would be called bromite. What about iodine with 1 oxygen and a 1- charge? Of course, we are in group 7. We will add up to -1. The 1 oxygen in the compound has a -2 charge, so +1 is what goes in the blank. So certainly not answers D or A. And this is the lowest positive oxidation state of iodine, so remember we get a hypoiodite start. So most students do this by sort of memorizing when they're in group 7. And I'm going to use X to represent the halogen. If it's XO4-, then it is a per8. If it is XO3-, it's an 8. If it is XO2-, it's an ite. And if it is XO-, it is a hypoite. And that formula works very well for things with chlorine, bromine, iodine, and oxygen. All right, now it's time to put an entire ionic compound together. So first we're going to start with the main group metals, which are group 1, group 2, and essentially aluminium. For a main group cation, we do not need to specify the oxidation state with a Roman numeral. It's obvious that sodium's in column 1, it's going to be +1. So there's no oxidation state variety. The same thing with magnesium, it will only be +2 in an ionic compound, and aluminium would be +3. So there's no need to give extra information to give the person who's learning the name the oxidation state. Now, as far as the anions that we have here, they are monoatomic anions, so we can just have the ending as -ide. So that first compound is just sodium sulfide. There is no reason to tell a chemist that it has 2 sodiums. Chemists will know sodium is +1, Sulfide is going to be 2-. Clearly there's 2 sodiums with the sulfide. The next compound is magnesium sulfide. There's no reason to tell a chemist that it's 1 magnesium. We know, because we know what the typical oxidation states are. And the last compound? Just aluminium oxide. No reason to tell anyone there's 2 aluminiums or 3 oxygens. If you know the oxidation states, you know what the neutral formula has to be for the ionic compound. But what about transition metals? Well, a lot of those can have different oxidation states. Some are +2, some are +3, some are +1. So what we do with those is we have the metal name unchanged, but we're going to use Roman numerals in parentheses to indicate the oxidation state. We'll start this with simple monoatomic anions, which have an ending of "-ide". So let's look at Fe2S3. This is going to be called iron with an oxidation state sulfide. How do we get the oxidation state? Well, we recognize that sulfur is very likely -2. Therefore, the iron has to be an oxidation state of 3. So this would be called iron 3 sulfide. Now, caution, it's very common for students to use 2 as a Roman numeral because they see that, there's a subscript of 2 right here on the iron, so I should call this iron 2 sulfide. No. Remember, the Roman numeral is the oxidation state. Now, there are some transition metals that really do not have variety. So do not use Roman numerals for zinc, silver, or cadmium. There's just no variety in these particular transition metals. So if you come across Ag2S, that is just called silver sulfide. Now, I am certain that if you search the internet, you could come up with silver parenthesis Roman numeral 1 sulfide. But remember, this is the official IUPAC naming tradition, and so these exceptions do not need Roman numerals. What about some of these unusual group 3, 4, and 5 metals that are very heavy? For these, we're going to list the metal name, but we will also use a Roman numeral to give us our oxidation state. So, for example, indium chloride. This is a group 3 very heavy metal. We would definitely want to specify the oxidation state, and of course it is 3 because it's with 3 chloride ions. If we had indium with 1 chlorine, it would be oxidation state +1 and get a Roman numeral of 1. So, here's some examples. Name the following compounds. Cobalt with chlorine. Cobalt is a transition metal. I think we're going to have to specify its oxidation state. So chlorine would be -1, and the cobalt in this compound would be +2. So we would call this cobalt 2 chloride. Copper with fluorine. Okay, once again, this is a transition metal, so fluorine would be -1, copper would be +1. We would call this copper 1 fluoride. And don't forget, I am still using the "-ide" ending for my anions because they are monoatomic anions. So remember, we use Roman numerals for the oxidation states of all metals, except for things in column 1, things in column 2, aluminium 3+, silver 1+, zinc 2+, and cadmium 2+. So Roman numeral anything you like except for those particular items. So let's look at titanium with 4 bromines. Titanium is main group metal or transition metal? I think it's a transition metal if you're watching this and also looking at your periodic table. So This is a transition metal. So therefore I need Roman numerals. So definitely not that. Definitely not that. Remember, bromine is a monoatomic anion, so that gets the "ide" ending. And of course, the oxidation state of the titanium is going to be +4. So I like the idea of D, titanium 4 bromide. Strontium and oxygen. Please look at your periodic table. And what you're going to find out is that strontium is in group 2. So if it's in group 2, it's +2. We don't need to specify the oxidation state. So goodbye to those answers. We don't need to let people know strontium is +2. We can just call that strontium oxide, and we're good to go. What about some of the other polyatomic ions, if they are anions involved in our compounds? Well, some memorization is required. Hopefully, you recognize NH4 as a cation, Cl- as an anion, and that's just going to be ammonium chloride. Hopefully, you look at the SO4 and you say, hey, wait a minute, didn't I just see an example where there was an SO4 2-? Yes. And magnesium is a main group metal. So we don't need to specify the oxidation state. This is just going to be magnesium sulfate. If you see SO3, hopefully you look at that and say, hey, didn't I just see an SO3 2- as a polyatomic ion? Yes. And manganese is a transition metal. So I am going to need Roman numerals for this. And of course, if the SO3 is 2-, then the manganese must be 2+. So this is manganese 2, and this would have an "ite" ending, so it is sulfite. Next one, NO3. NO3 is a polyatomic ion with a 1- charge that has the name nitrate. And zirconium is, of course, a transition metal. So I would have to say that if there's 4 nitrates with it, it's probably got an oxidation state of +4. So we should call that zirconium 4 nitrate. OH. Hopefully you recognize OH as, that's hydroxide. Tin is one of our heavier main group metals. So it's what I would call a heavy main group. So we are going to have to give it an oxidation state because it's not one of the simple ones that's always predictable. So we will call that tin 2 hydroxide. So let's take a look at this one. Hopefully you're looking at NH4 and saying, didn't I just see that? Isn't that ammonium? So it's not ammonia, okay? Ammonia is NH3. You have NH4+, so not that one. We don't have to say how many. We really do not. Not when we're dealing with ionic compounds. So triammonium is not it. So we're down to C or D. All right, is that a phosphate or a phosphite? Let's check. PO4, probably a 3- because it's with 3 1+ ammoniums. So each oxygen is -2. So something -8 equals -3. That something is +5. All right, and of course, phosphorus is in group 5, so we have a match. And when we have a match, the ending is 8. That is ammonium phosphate. All right, how about this one? Vanadium is going to be a transition metal. So we need to specify the oxidation state. So if each oxygen is -2, probably each vanadium is +5. So Not that one. We don't have to specify no dies, tries, or pents. It is oxidation state +5. Yeah, no pents there either. So I do believe we're here to vanadium 5 oxide. Calcium is a main group metal. We don't need any Roman numerals, so goodbye, goodbye. Now it's just a matter of deciding, is the SO4 a sulfate or a sulfite? The calcium's going to be +2. The SO4 is going to be a 2-. So when we look at the SO4 2-, of course it adds up to -2 charges. Each oxygen's -2, so it's -8. Something -8 is -2, so that's a +6. And sulfur is also in group 6. So when we have a match, we have an 8. So that would be calcium sulfate. How about this one? Thallium with oxygen. Okay, thallium, if you check your periodic table, is going to be a heavy main group element. So I think we're going to need an oxidation state. So each oxygen is -2. That's going to make the thallium a +3. So not that one, not that one. And we don't have to say try. Just thallium 3 oxide is enough for a chemist to put that together and know what the compound looks like. Now, just a reminder for these polyatomic ions, they are clusters of atoms that have a 2- charge overall. So if you were asked to put together a compound between aluminium 3+ and SO4 2-, we are just going to crisscross the charges, just like we always did, okay? But since we have a group of a polyatomic, we are going to group that sulfate together to indicate that we have 3 sulfate units. So use parentheses if you have more than one polyatomic in your ionic compound. On the other hand, if we want to make a compound between calcium and sulfite, first, when we crisscross, we would have a subscript of 2 for them, but of course we can simplify. Once we are down to 1 polyatomic, you do not need parentheses. So that is just CaSO3. Now, if you do Google your naming homework, you're going to come across an older tradition of naming. There was a time when poor chemistry students had to memorize the high and low oxidation states of the transition metals. And for example, if we dealt with iron, which has a +2 oxidation state, it would have an us ending and be ferrous chloride. Iron with a +3 oxidation state would have an ic ending and be ferric chloride. So I think the IUPAC naming convention is a lot clearer for students. And we would simply call +2 oxidation state iron 2 chloride and +3 oxidation state iron 3 chloride. Okay, we have now finished chapter 4, talking about ionic materials and ionic bonds. It's time to start on chapter 5, where we deal with covalent or directional types of bonds. So we're actually going to go back to Coulomb's law when we think of covalent bonds in molecular compounds. And you may remember that there's a relationship between charge and the distance between them. So let's imagine 2 hydrogen atoms. Nucleus is in the center, electrons around the outside. And let's start pushing them closer together. And what you're going to find happens is that the electron of one atom sees the nucleus of the other atom. And that would be opposite charges attracting, so they're going to fall down the energy well. And we'll keep falling down the energy well until the electrons are very effectively between the two positive nuclei. Now at some point, we're going to get the nuclei too close, and then the two positive charges are going to repel. So there is sort of a minimum energy when two atoms meet up, and a perfect distance. So for the hydrogen molecule, the perfect distance is a 0.74 angstrom bond length, and the energy released when those two hydrogens come together is known as the bond energy, and that is minus 436 kilojoules per mole of hydrogen. So think of the two electrons between the nuclei being shared and buffering the two positive nuclei from each other. So when we think about two hydrogen atoms getting together, we're going to draw the atomic symbol, which is hydrogen, with a dot next to it. And this is what's known as a Lewis symbol, where the dots represent the number of valence electrons. The two electrons would get between the two hydrogen nuclei, and we would just draw two hydrogen atoms with a line between them. So a line between element symbols means a pair of electrons. Two electrons shared between the atoms. And this we call a covalent bond. Now, when we think of sharing between two hydrogen atoms, they have the same electronegativity, so they're going to share equally. Both of them have a chi of 2.2, so their difference in chi is 0. There is no electronegativity difference, so each hydrogen is equally attractive to the electrons. We have equal sharing. That's known as a covalent bond or non-polar bond. What if we had something like lithium and fluorine, though? Lithium is a metal, fluorine is a nonmetal. So we're going to not share equally. We're going to make an ionic bond where the electrons are transferred from lithium to fluorine. The nonmetal is more electronegative, so it's going to take the electron. So we're going to bind up with lithium 1+ and fluorine with a 1- charge. And if we look at the electronegativity difference, on the chart you can see that lithium has an electronegativity of 1 and fluorine has an electronegativity of 4. So the delta chi, 4 minus 1, is going to be 3. When we think of this in terms of valence electrons, there's a huge electronegativity difference. Fluorine is much more attractive to the electron, so we're going to form an ionic compound. So this is complete electron transfer and an ionic bond. Now these are kind of the two extremes. If delta chi is less than or equal to 0.4, we call that a covalent bond. That would be hydrogen to hydrogen. If delta chi is greater than or equal to 1.8, we would consider the bond ionic. And that would be the lithium fluoride example with an ionic bond. But what if it's in between? What if delta chi is less than 1.8 but greater than 0.4? What do you get? Well, we can show the example with hydrogen and chlorine. The delta chi is 1 between those two. So that's well within our range of not quite ionic, but also not quite covalent. So chlorine is not electronegative enough to take hydrogen's valence electron completely away from it, but it is going to hog it. So we might think of this as hydrogen and chlorine with the electrons between them, but you notice I've got the electrons a little bit closer to the chlorine than there are to the hydrogen. So what that results in is partial positive and partial negative charges. The hydrogen's a little bit positive because its electron is being used more by chlorine. It's in chlorine's realm of influence much more than it is in hydrogen's, and the chlorine is going to be partially negative. So since there are two poles in this bond, it's called a polar covalent bond. And it can be drawn with not only a line, but an arrow tip that points to the chlorine and a little crosshatch that lets us know which atom is going to be more positive. So this is known as a bond dipole, and you're going to see this in Chapter 7 where we look at bond dipoles and look at overall polarity of compounds. And the trick to these arrows is to point at the electron hog. So this means there is some electronegativity difference. So the electron is attracted to chlorine, but it still visits hydrogen. I guess this would kind of be like if hydrogen and chlorine got a divorce and the dog got to sometimes visit hydrogen and sometimes visit chlorine. So hydrogen would be a little partially positive because they don't fully have the dog. And chlorine would be a little bit negative because apparently chlorine has 5 dogs plus the one that gets to visit it from time to time. So this would be unequal sharing and a polar covalent bond. And this is when delta chi is between 0.4 and 1.8. And so to summarize all this on the same screen, if we have very little difference in electronegativity, we call that a covalent bond. If we have a large difference in electronegativity, we call this an ionic bond. And if we have a bit of difference in electronegativity, we call this a polar covalent bond that has unequal sharing. And this concludes Lecture 10.